Here we go. So unit 9 is called the mole, and the mole, or this unit, is going to cover one standard. So let's talk about what a mole is. So a mole is the quantity of a substance that contains the same number of particles as our atoms in exactly 12.000 grams of carbon-12. So we use carbon-12 as a standard when we talk about moles. And please do not get all caught up on what a mole exactly is. A mole is just a unit. It's there to tell us how much of a substance we actually have. Okay, so just treat it like liters or grams. It's just a unit. 1 mole is considered to be equal to the molar mass of the substance. So what is molar mass? Molar mass is the amount of grams in 1 mole of a substance. The units, therefore, are grams per mole. It's represented by the atomic mass of an element, so it's the mass number on the periodic table. Water, for example. Well, the molar mass of water is 1.01, and we have 2 of those, so we're going to multiply that by 2 to give us 2.02. And then oxygen has a molar mass of 16. So we're going to take 2.02 and we're going to add it to 16 to give us a total molar mass of 18.02 grams per mole for water. HCl. So again, H is 1.01, chlorine is 35.45. So we're just going to add those two numbers together to give us a total molar mass of 36.46 grams per mole. Now here's a tricky one. So we have magnesium oxide. So magnesium has a molar mass of 24.31. And then we have OH in parentheses. So we're going to add OH together. So 16 plus 1.01. And we're going to multiply that by 2 since we have 2 hydroxides to give us a total mass of 34.02. And then we're just going to add 34.02 to 24.31, and it's going to give us 58.33 grams per mole for magnesium oxide. And now we have calcium phosphate. So calcium has a molar mass of 40.08, and we have 3 of those to give us a total mass of 120.24 for calcium. Again, PO4 is in parentheses, so we're going to treat it as one thing. So we're going to do 30.97 for phosphorus plus 16 times 4. The 4 is because we have 4 oxygens. And we're going to combine those two masses and multiply it by 2 since we have 2 phosphates. And that's going to give us a grand total of 189.94 for the molar mass of the 2 phosphate groups. And then we're going to add the phosphate to the 3 calciums to give us a molar mass of 310.18 grams per mole. And then we have carbon dioxide. So carbon is 12.01, and we have 2 oxygens, so 2 times 16 is going to give us 32. And we're going to add those two together to give us a total molar mass of 44.01 grams per mole for carbon dioxide. Go ahead and try these on your own, and we're going to go over the answers in class. Here we have a mole conversion triangle. So these are just like conversions that we did at the beginning of the year. The easiest way to remember the mole conversion triangle, is to realize that mole is in the middle. So anytime we're going to convert to moles, we're going to divide. And anytime we're going to go to mass, particles, or volume, we're going to multiply. So an easier way to remember that is what we call DIMO. Divide in, multiply out. Mole conversions. So we're going to do some moles to mass, or grams. So we need to calculate the molar mass of the substance. Anytime you see the word mass or grams, you need to think molar mass. And then we need to calculate the molar mass. And again, 1 mole is equal to the mass of the substance. We're going to go over these examples in class, but if you want to try them out on your own, that would be good for you. And then we have moles to volume, or liters. So 1 mole is equal to 22.4 liters. That is a constant. Anytime you see the word volume or liters, you need to write down or think of 22.4 liters. And then we have moles to particles. So 1 mole is equal to 6.022 times 10 to the 23rd particles. And those particles can be formula units, molecules, atoms, ions, etc. And we call this number Avogadro's number. If you look in your reference packet on page 1, it's the very first thing that's there. So you don't have to memorize this number. Again, this is called Avogadro's number. So it's the number of particles in 1 mole of a substance, and this never changes. Again, we're going to do these mole conversions in class. So now we get to percentage composition. Percentage composition is just a percentage of mass of an element in a compound. The formula is the molar mass of the element over the total molar mass of the compound. So think about it in terms of it's the part over the whole. So if I have $1 and realize that 1 out of my dollar is a quarter, because it takes 4 quarters to make $1. So if I have 2 quarters, then I have 2 out of 4, which would give me 50 cents of $1. So just think of it again as part over the whole. Examples we're going to go over in class, and then you're going to have practice. Empirical formulas. So empirical formula is the simplest whole number ratio of a compound. So this is where if we're given a formula and we can reduce the subscripts, we're going to do that. So we'll reduce the subscripts all the way down as far as they can go to give us an empirical formula. So for example, hydrogen peroxide, H2O2, is not an empirical formula because we can reduce those two 2's down to 1 and 1. So we would get HO. So determine if the following are empirical formulas. So yes or no. So number 1, H2O. Well, so we cannot reduce 2 and 1 down any further, so no. So yes, that is an empirical formula. Number 2, C6H12O6. No, that is not an empirical formula because we can reduce that to CH2O. Number 3, C11H22O9. Yes, that's an empirical formula because we cannot reduce those numbers. Number 4, BCl3. Yes. Number 5, N2O2. No, because again we can reduce the 2's down to 1, so we can get NO. That's the empirical formula for number 5. Number 6, N2O. Yes, that's an empirical formula because we cannot reduce 2 and 1 down any further. So in order to determine the empirical formula, you're going to be given the percentage composition in either grams or a percent. So step number 1, if you're given the percentage composition, we're going to change the percent to a G. So basically changing the percentage to a gram. We're going to assume we have a 100-gram sample, so that's why we can just change it to a G. And then you're going to divide each mass from step number 1 by the element's molar mass. And we're going to keep at least 5 decimal places. The more we round, the more our answer is going to be off. So we want to be as specific as possible and keep as many decimal places as we can. Step number 3, you're going to divide each number from step number 2 by the lowest number from step number 2. And we're going to go over some examples to see how this plays out. Now there are some special circumstances that you have to know. So if a number from step 3 ends in 0.25, we're going to multiply everything by 4 in order to give us a round number. If it ends in 0.33, we're going to multiply everything by 3. If it ends in 0.5, we're going to multiply everything by 2. If it ends in 0.75, we're going to multiply everything by 4. The other numbers you can just round, so either round up or round down. Example number 1. An oxide of nitrogen is found to contain 69.6% oxygen. What is the empirical formula? Well, we're going to have 69.6% oxygen, so we're going to change the percent to a G. So we're going to have 69.6 grams of oxygen. If we have 69.6% oxygen, how much nitrogen do we have? Well, we're just going to take 100 minus 69.6 to give us 30.4% nitrogen. And again, we're just going to change that percent to a G, so we're going to have 30.4 grams of nitrogen. Step number 2 is to take the mass of each element and divide by its molar mass. So we're going to take 69.6 grams of oxygen and divide it by 16.00 grams per mole. And we're going to get 4.35 moles. Do the same thing for nitrogen, and we're going to end up with 2.17143 moles. Remember, for step number 2, we want to keep as many decimal places as we can. So you can see for nitrogen, we kept 5 decimal places. Step number 3 is to take the two numbers for oxygen and nitrogen that we did in step number 2 and divide by the lowest one. Well, between 4.35 and 2.17143, the lowest one would be 2.17143. So we're going to take oxygen's number, 4.35, and we're going to divide it by 2.17143 to give us 2. And we'll do the same thing for nitrogen to give us 1. So now we're just going to combine them together. So we have 1 nitrogen and 2 oxygens. Example number 2. A compound is 24.7% calcium, 1.2% hydrogen, 14.8% carbon, and 59.3% oxygen. Write the empirical formula and name the compound. So step number 1, we're going to take all of our percentages and convert them to grams. So 24.7% calcium becomes 24.7 grams of calcium. 1.2% hydrogen becomes 1.2 grams of hydrogen. 14.8% carbon becomes 14.8 grams of carbon. And 59.3% oxygen becomes 59.3 grams of oxygen. Step number 2 is to divide each element's mass by its molar mass. So for calcium, we're going to take 24.7 grams and divide it by 40.08, and that's going to give us 0.61627. And we're going to do that for hydrogen, carbon, and then oxygen. And step number 3, again, is to divide by the lowest number from step number 2. In this case, it's going to be calcium's number of 0.61627. So we're going to take that and divide it by all of them. So calcium would give us 1, hydrogen would give us 2, carbon would give us 2, and oxygen would give us 6. So what is the answer? Well, you would probably want to write CaH2C2O6. But H2C2O6 is not one of your polyatomic ions. But we can pull a 2 out. If we pull a 2 out, then we get HCO3, which is hydrogen carbonate. So we're going to get CHCO3 2. So calcium hydrogen carbonate, or calcium bicarbonate. And we can do that because we know the charge of calcium is 2, which means we need 2 on the outside. So that's where that 2 comes from, on the outside of hydrogen carbonate. You won't have anything this difficult to complete. We're just showing this as an example. You're going to practice some more in class. And then we get to empirical or molecular formulas. Molecular formulas are considered to be the true formula of a compound. So for example, from the empirical formula, I gave you H2O2, which would be an empirical formula of HO. Well, that's not hydrogen peroxide. Hydrogen peroxide's true formula is H2O2, which is a whole number multiple of the empirical formula. So you must be given the molecular or molar mass of the compound. Now you're going to take the molecular mass and divide it by the empirical molar mass, which is going to give you a whole number. And then you're going to multiply that whole number to each element in the empirical formula. But realize that sometimes you're going to have to find the empirical formula first. So you're going to have to go over the steps that are involved in finding empirical formula. Example number 1. The empirical formula of a compound is P2O5. The molar mass of this compound is 283.89 grams per mole. What is the compound's molecular formula? Well, we're going to take our molar mass. We'll find the empirical mass first, which is 283.89 grams per mole. So that goes back to finding the molar mass of a substance. So 2 phosphorus and 5 oxygen. Well, the molecular mass is 283.89. I'm going to divide that by the empirical mass, which is 283.89, to give us 1, which means the empirical or the molecular formula is P2O5, which is the exact same thing as an empirical formula. So the empirical formula and the molecular formula can be the same thing. It doesn't always have to be different. So example number 2, determine the molecular formula of the compound with an empirical formula of CH and a molar mass of 78.110 grams per mole. So we're going to take our molar mass of 78.110, and we're going to divide it by the empirical molar mass of 13.02 grams per moles, and that's going to give us 6. So we're going to take that 6 and we're going to multiply it throughout the compound, and it's going to give us C6H6. So in this case, the empirical formula would be CH, and the molecular formula would be C6H6. But we can reduce, again, C6H6 down to CH to get its empirical formula. And we'll practice more in class. The last part of this is the formulas of hydrates. Remember that hydrates are a compound that contains water molecules. Okay. And anhydrous is a compound without the water molecule, so it's the ionic salt. So steps to determine the formula of a hydrate based on laboratory data, and we're going to do a lab where we have to find the formula of a hydrate. So we're going to do these to get the data, do this type of lab. The first thing you're going to do is divide the amount of water by 18.02 grams per mole, because that's the molar mass of water. So if we divide the amount of mass of water by its molar mass, we're going to get moles. Step number 2, divide the amount of the anhydrous by its molar mass. Step number 3, divide each number by the lowest one, and this should be the anhydrous, because we only want 1 mole of the anhydrous. And then we're going to write the formula. So I'm going to go over these examples in class, but you should try them. They're pretty easy. It can be complicated, but just follow my steps and you'll be fine. And then we're going to practice more of these in class as well.